All right, 2.5, the fundamental theorem of algebra. So, what is the fundamental theorem of algebra? It states that, let's say that the highest power of f of x is n. Right, that's the highest power. Then, the polynomial function has n zeros. Okay, so wherever the highest power is, that's how many zeros you have. Similarly, with the linear factorization theorem, we're going to state again, this is linear factorization, LFT, we'll call it. F of x is a polynomial of degree n. Then f of x has n linear factors. Okay? Given that all those factors are going to be complex numbers, right? Of some kind of form, x minus a number, x minus a number, etc., etc. All right, so here, this is called the rational root theorem, okay? Rational root, not root theorem. And let's say we have this polynomial function up here, right? The a sub n's, the a sub n minus 1s, they just represent our coefficients of each of these terms down the line, okay? We are going to be talking about p and q, okay? P refers to the factors of a sub 0. A sub 0 is the number, the constant, one that doesn't have any x attached to it. The a sub n, or q's, the factors of a sub n. Okay, a sub n is the leading coefficient, meaning the term in front of the highest power. Sometimes it's 1. It's nicer when it's 1 because it makes our lives easier with this problem. And what we do with these is all the possible rational zeros of the function. Rational zeros. Now, let's talk for a second before I get into this. Why would we have this rational root theorem? Our goal with this is that sometimes we can't factor things, okay? Sometimes it does not work out. So what we can do is use the rational root theorem so that we can find out what our possible zeros can be. So possible rational zeros are going to be our p's over our q's. P being factors of the constant term a sub 0, and q's being the factors of the leading coefficient a sub n. So we have this polynomial function right here, and let's find the rational zeros of this function using the rational zeros test. So the factors of the constant, factors of 6 is 6, 3, 2, and 1. Factors of leading coefficients 1, so it's going to be plus or minus 1. So therefore, we will be testing these values. And remember the factor theorem we learned earlier in this chapter. If any value, we can plug in any value and it comes out to be 0, that's going to be a factor. So what we're going to do is we're going to take all 8 of these possibilities and plug them into this function. What I recommend you do, because that could take a while, you're like, oh no, that's going to take forever, Mr. Warden. Well, guess what? You can use your calculator, put this term in for f of x, and then plug all 8 of these into your table, okay? So, if we were to plug all 8 of those into your table, your answers will be -1 will work. Because what we're looking for when we plug these in, if you get an output of 0, it's a factor. So -1 works. Also, -2 also works, and 3. So we have 3 solutions for this, okay? And we know there aren't any more because, as we went over in the first slide, since the highest power is 3, how many zeros should we have? 3. So we did. Yay. Same rule. Let's do the rational zeros test and roll. Let's see. So the factors of the constant is just 1, plus or minus 1, lucked out. The leading coefficient, we have plus or minus 2 and plus or minus 1, giving us possible rational zeros of plus or minus 1/2 and plus or minus 1. Let's see what happens. When we put in -1, that works. Right? And then any other zero will be -1/2. Okay? So what we're going to be doing in future problems is I'm going to show you how to find what the last zero is, right? And I'll give you a little hint. In this case, we can tell easily that either this one or this one will have a multiplicity of 2. I don't know which one, but one of them do, but I'll explain in the next slide how I know that. So I know this because of our complex conjugate rules. Complex conjugate says that if a plus bi is 0, then a minus bi is also a 0. Now, what does that mean for us? Why did that prove to me that that it had to be a real 0 for that last problem? Anytime we have an imaginary 0, we're going to have 2 imaginary zeros. Anytime we have 3 imaginary zeros, we're going to have a 4th, right? So you're always going to have an even number of imaginary zeros. So I had one more 0 we couldn't find in the last problem, so we knew it had to be real. Okay? It couldn't be imaginary. So let's do an example with this fact. I'm going to give you the polynomial f of x equals x cubed minus 7x squared minus x minus 87 and a 0 of 5 plus 2i. Okay? We need to find the other zeros based off of this 0. Okay? So your book has one way of doing this. I have a different preference. Okay? If you do not like the way I'm doing this, you may use the book method. That's fine. You may not like the book method though either. So I like this. So what we're going to do is synthetic division. Okay, so I'm going to divide out that 0. Keep the 0 the same sign as it's given. Now, if I give you a factor, let's say like I gave you x plus root 3, then you're flipping the sign and putting in negative root 3. But in this case, if I give you the 0, keep the sign the same. Bring it down to 1, multiply, get 5 plus 2i, giving you negative 2 plus 2i. You FOIL these two being this times this, giving us, if I FOIL that, would be negative 10 plus 10i minus 4i minus 2i squared. Or plus 2i squared, rather. Oh, what am I doing? It's 2 times 2 is 4. Plus 4i squared. So that's going to get us, in this little box, negative 14 plus 6i. And then when I add that, I'm going to get negative 15 plus 6i. And then FOIL again. I'll use red this time to FOIL. And it's going to get us 5 times negative 15. That will get us negative 75. And then we're going to get plus 30i minus 30i plus 12i squared. 30i, that's right, lucky us. Or else we would have got the problem wrong. So, and then we're going to get negative 75 minus 12, which is negative 87. And I just remembered the problem was supposed to be plus 87 here. And so this should have been plus, and then we end up getting a 0, so it is a factor. Now, here's where your complex 0 rule comes into play. I'm going to take these values right here and do synthetic division again, but this time with the other 0 we know about, which is 5 minus 2i, right? Because we have 5 plus 2i. By a complex conjugate rule, we also have 5 minus 2i. So let's go to the next page, and we'll do that. All right, so let's get the other 0. If you do these right, these will work out every time, okay? So bring down the 1, and we multiply 5 minus 2i, and look how it worked out. The i's cancel, so we're left with 3. Multiply again, we get 15 minus 6i. Look, we get 0. Hooray! So we get x plus 3 as our other factor. Set it equal to 0 and solve. X equals negative 3 is the other 0. So our zeros are going to be 5 plus 2i, 5 minus 2i, and negative 3. So those are 3 zeros by using the rational root theorem. All right, so we're going to do a combination of everything, all right? So we're going to use the rational zeros test to find the rational zeros and then find any remaining ones that we have left over. So we got to find the factors of 16 over factors of 1, because 1 is the leading coefficient, 16 is the constant. And that's just going to get us plus or minus 16, plus or minus 8, plus or minus 4, plus or minus 2, plus or minus 1. Okay, so we have 10 to test out, so we're going to do that in our calculator. The only 0 I'm seeing, which is a little worrisome, is 2. So let's do what we did before, synthetic division. 2, 1, negative 4, 8, negative 16, 16. Bring down the 1, 2, negative 2, multiply, get negative 4, add it, get 4. 4 times 2 is 8. Add it, get negative 8, get negative 16, 0. We have x cubed minus 2x squared plus 4x minus 8. Now I'm a little less worried now because I noticed one thing, and that's we can do factor by grouping. X squared times quantity x minus 2 plus 4 times quantity x minus 2. Factor out the x minus 2, and look. So we have 2 with a multiplicity of 2, so that's part of the reason why we only found one rational 0. And then the other one is x squared plus 4. And when we find the zeros of that, we get x equals plus or minus 2i. Because whenever we subtract 4, square root, you're going to get plus or minus 2i. So your zeros are going to be x equals 2, multiplicity of 2, x equals 2, and 2i rather, and negative 2i. So those are your zeros. Appreciate watching, and we'll see you later.